on developing this terminology because it's going to make life a lot easier for us in what follows. So we'll say that a matrix is in the echelon form if it satisfies three conditions. First condition is if there are any zero rows. A zero row is one in which every element is zero. So if there are any zero rows, they are grouped together at the bottom of the matrix. If there are any zero rows in the matrix, they should be grouped together at the bottom of the matrix. Then, the first non-zero entry in every non-zero row is 1. We call this element the leading element. It's like a leader for that row because in that row it is the first non-zero element. And third condition is regarding the position of these leading elements. It says in any two successive non-zero rows, the leading one of the lower row is always to the right of the leading one in the upper row. So let me once again explain what are the three conditions for a matrix to be in echelon form. If there are any zero rows, that means rows consisting entirely of zeros, they should be found at the bottom of the matrix. What we mean more importantly by this is, if there are any zero rows, they should not be found somewhere in the middle or at the top of the matrix. They have to be necessarily at the bottom of the matrix. If there are no zero rows, then this condition does not apply. All we have to ensure is that if there is a zero row, it should not be in the middle or at the top. So if there are any zero rows, make sure that you find them at the bottom of the matrix. Then look at any non-zero row. The first non-zero entry in such a row should be 1. We will call it the leading element. And the third is regarding the position of the leading elements. In any two successive non-zero rows, the leading one of the lower row should be to the right of the leading one in the previous row. It's again going to be a little difficult to just leave it in this form and understand it. So it's best to look at a few examples. So let's take this matrix 1, 4, minus 3, 0, 1, 2, 0, 0, 0 and check whether the conditions are satisfied. Firstly, notice that there is a row consisting entirely of zeros. That means there is a zero row and it is at the bottom of the matrix. So condition 1 is satisfied. Then look at the first non-zero entry in this row. It is 1. This is the leading one for the first row. Similarly, the first non-zero entry in the second row is also 1. So in a non-zero row, the first non-zero entry is 1. That's why the second condition is satisfied. And third condition is, if we take any two non-zero rows, the leading one in the lower row is somewhere to the right of the leading one in the upper row. So as we go down, the leading elements should go on shifting to the right. Since all three conditions are satisfied, this matrix is said to be in the echelon form. Let me give you some more examples. be immediately to the right. The leading one of the lower row should be somewhere to the right of the leading one in the previous row. So third condition is also satisfied, and that's why this matrix is also in the echelon form. Let's take one more example. Look at this matrix. Now in this matrix there are no zero rows. The first condition says only if there are zero rows, make sure that they are at the bottom. If there are no zero rows, we will say that this condition is trivially satisfied. And the second condition is also satisfied because the first non-zero element in every row is 1. Also, the positions are perfect. So third condition is satisfied. That's why this matrix, these three are matrices in the echelon form. However, look at the matrix D. This matrix is not in the echelon form because there is a zero matrix. There is a zero row in the matrix, and it is not at the bottom of the matrix, it is somewhere in between. So this matrix, for this matrix, the first condition is not satisfied, and that's why this is not in the echelon form. Next, let me take the matrix 1, 4, minus 5, 0, 2, 1, 0, 0, 0. Now, the zero row is at the bottom of the matrix. However, if you look at the first non-zero entry in the second row, it is not 1. And that's why second condition is not satisfied. And hence, this matrix is not in the echelon form. Also, if I take the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1, first condition does not apply because there is no zero row. The first non-zero entry in every row, in every non-zero row is 1. However, the positions are not correct. The leading element in the second row is actually to the left of the leading element in the previous row. This is not allowed. And therefore, these are examples of matrices which are not in the echelon form. So this is regarding the echelon form of a matrix. Now we will see how to reduce any matrix towards echelon form. And to do that, we require what are called as elementary transformations. Before I go ahead, let me add over here that this echelon form is also called row echelon form because all the conditions have to do with rows of the matrix. One could, of course, if one wants to really be very specific, one can also define column echelon form. So right now we are really concentrating on the rows of the matrix. So what I have defined is the row echelon form or simply the echelon form of a matrix. To reduce a matrix to the echelon form, as I mentioned, we require elementary transformations. So let's quickly list the elementary transformations. What I am listing here are the elementary row transformations. Similarly, one can also perform elementary column transformations. There are 3 elementary row transformations that we can perform on a matrix. The first is Rij. Here we interchange the ith and the jth row. So Rij will stand for interchanging the ith row and the jth row of the matrix. The next transformation that we are allowed to perform is K times Ri, where of course K is not equal to 0. K is a non-zero scalar. Here we are multiplying the elements of the ith row by the scalar k. So this is the second type of row transformation that is allowed, and the third is Ri plus k times Rj. In this transformation, to the elements of the ith row, we add k times the corresponding elements of the jth row. So in Ri plus k times Rj, to the elements of the ith row, we add k times the corresponding element from the jth row. So these are the three elementary row transformations. In exactly the same manner, one can define elementary column transformations. Now let us see how we can use elementary row transformations to reduce a matrix to the echelon form. So let's start with the problem. Reduce each of the following matrices to the echelon form. Let's try out the matrix 1, 2, 3, 4, 5, 6, 7, 8, 2, 1, 5, minus 1. So let us try and reduce this matrix to the echelon form. The first step while reducing a matrix to the echelon form should be to bring a 1 in this position. Make sure that you somehow get a 1 in this position. Now, to begin with, there is a 1 in this position, so I don't need to put in any extra effort to bring a leading 1 in the first row. The next step will be to bring zeros below the leading 1. That means I need a 0 in this position and a 0 in this position. So the transformations that I am going to use are, I need a 0 in the second row. So I will be doing R2. Always use the opposite side. So it will have to be R2 minus 5R1 to get a 0 in this position. And to get a 0 in this position, this is in the third row. Use opposite side. I need R3 minus 2R1. It's the second row and the third row which is undergoing a transformation. First row will remain as it is. The second row is changing. The third row is changing. So let's do the calculations. R2 minus 5R1, 5 minus 5, 0. 6 minus 5 into 2, 6 minus 10. 6 minus 10 will give us minus 4. Then we have 7 minus 5 into 3, 7 minus 15, that's minus 8. Then we have 8 minus 5 into 4. 8 minus 20. 8 minus 20 is minus 12. Now let's go to the third row. It is R3 minus 2R1. So it will be 2 minus 2, 0. 1 minus 4, minus 3. 5 minus 6, minus 1. Minus 1 minus 8, minus 9. So the first step is to bring a leading 1 in this position. After that, bring zeros below that leading 1. Now, you can as good as forget the first row. Now, let's concentrate on the second row and do something similar. Now, next, I need to bring a leading 1 in the second row. So, in this place, I need to get a 1. So, the best transformation to perform will be to divide the second row by minus 4. So, let us perform the transformation. Minus 1 upon 4 times R2. So I'll get 0, minus 4 upon minus 4 is 1, minus 8 upon minus 4 is 2, and this will be 3. After getting a leading 1 in the second row, we need to get a 0 below that. So I'll need to do R3 opposite side plus 3 R2. At this stage, plus 6 is 5 and minus 9 plus 9 is 0. And the final step is to get a leading one in the third row. That should be easy now. All I have to do is to divide the third row by 5 or to multiply the third row by 1 upon 5. So I'll get 1, 2, 3, 4. 0, 1, 2, 3. 0, 0, 1, 0. So this is how we reduce a matrix to the echelon form. Let's try out one more example. Let us reduce this matrix also to the echelon form. We just clear off all this. So if we go by the earlier procedure, the first step is to bring a leading one in this position. However, I have a 0 in this position. I cannot divide by 0. So I have to first interchange with some other row and get a non-zero element in this position, and then I can get a leading one in the first row. So let me interchange the first row with the second row. So that will give me 2, 4, minus 10, 6, 12, 28 in the first row. 0, 0, minus 2, 0, 7, 12 in the second row. I am interchanging the first row with the second row. Third row remains as it is. At least now I have a non-zero element in this position. So it should be possible to get a 1 in this position. And for that, I'll have to multiply the first row by half. So I'll get 1, 2, minus 5, 3, 6, 14, 0, 0, minus 2, 0, 7, 12, 2, 4, minus 5, 6, minus 5, minus 1. After getting a leading one in the first row, the next step is to bring zeros below that. I already have a 0 in the second row, so I need a 0 in this position. To get a 0 in this position, the transformation that I will require is R3. Since this is in the third row, use opposite sign, minus 2 R1. So I'll get 1, 2, minus 5, 3, 6, 14. First row remains as it is. Then second row is 0, 0, minus 2, 0, 7, 12. Then we have 2 minus 2, 0. 4 minus 4, 0, minus 5 plus 10, minus 5 plus 10 is 5, 6 minus 6, 0, then minus 5, minus 12, minus 5 minus 12, that is minus 17, and minus 1 minus 28, minus 1 minus 28, that will be minus 29. Next step will be to bring a leading one in the second row. So maybe I can divide the second row by 2. So this is one of the ways of getting a leading one in the second row. Another option would have been to do R2. I could have got a leading one in this position by doing R3 plus 2 times R2, got a 1 over here. And then I could have interchanged these two rows. So there are alternate ways of doing this. This is just one of the methods of getting a leading one in this position. So we'll have 0, 0, 1, 0, minus 7 by 2, and this will be, it's the same sign. I should have divided by minus half because I want to get a plus 1 over here. So let me do minus 1 upon 2 times R2. So 0, 0, 1, 0, minus 7 by 2, and this will be minus 6. Then we have 0, 50, minus 17, minus 29. And after getting the leading one, the next step is to bring a 0 below that. So I will need R3. Remember, at this stage, you have to make use of the second row. Otherwise, these zeros will go. So, second row as it is. It's only the third row which is undergoing a transformation. 5 minus 5, 0. This will be 0. This will be minus 17 minus 5 into minus 7 by 2. So that works out to be minus 34 plus 35 upon 2. That is half. So here I'll get half. And in the last place, I'll get minus 29 minus 5 into minus 6. That means minus 29 plus 30. Minus 29 plus 30 is 1. And now finally, we need a leading one in the last row. To get a leading one in the last row, let me multiply the last row by 2. We get 0, 0, 0, 0, 1. So that's the echelon form of this matrix. And next, we'll be defining the rank of a matrix. Now, before I go to the rank of a matrix, I must tell you how to find out the minor in a matrix which may not be a square matrix. So suppose I take a general m by n matrix by a minor of order r. By a minor of order r, what I mean is from this matrix select r rows and r columns. Select r rows, r columns. You'll get a submatrix which is going to be a square matrix that will have r rows, r columns. Then the determinant of this is called a minor of order r. So for a minor of order r, you have to select any r rows and r columns from that matrix and take the determinant of those selected rows and selected columns. So now we will define the rank of a matrix. The rank of a matrix is denoted by row of A, and we say that the rank is equal to R if the matrix has at least one non-zero minor of order R. In general, there can be many minors of order R because it's a question of which rows and which R columns you select. So you could have more than one minor of order R. Make sure that amongst all the minors of order R, at least one of them is non-zero, and every minor of order greater than R, every minor of order greater than R, every minor of order greater than R is 0. So if we go by this definition, it's going to take quite some time to determine the rank of a matrix. Because say even if we were working with a 3 by 3 matrix, what I'll have to do is to find minors of order 1, order 2, order 3 and then see for what value of R this condition is satisfied. So quite a lot of effort goes into finding the rank of a matrix if we just stay with the definition. Instead, I'll give you a working group, and as I mentioned, the echelon form is already there. So I'll give you an easier method of finding the rank of a the rank of a matrix is equal to number of non-zero rows is equal to number of non-zero rows in the echelon form of that matrix. We won't go into why this actually works, but this is a very nice method of finding the rank of a matrix. What you need to do is first obtain the echelon form of the matrix and then simply count the number of non-zero rows in that matrix. So let's try out an example. Say determine the rank of the matrix A equal to 5, 6, 7, 8, 6, 7, 8, 9, 11, 12, 13, 14, 16, 17, 18, 19. Now, the simplest way of finding the rank will be to first reduce this matrix to the echelon form. Now what I need to do is to get a leading one in this position, but one method of getting a leading one in this position will be to divide the first row by 5. But if I divide the first row by 5 and I am doing this mechanically, not using a computer, so I'll have fractions over here. And personally, I am not too fond of fractions, so I'll try and get an alternate method of getting a one in this position. In fact, there are two more methods. What we can do is do R2 minus R1. If we do R2 minus R1, we'll get 1. 7 minus 6 is 1, 8 minus 7 is 1, 9 minus 8 is 1. Yes, I guess that's going to make life a little easy now. Now I will interchange the first row with the second row. So I'll get 1, 1, 1, 1, 5, 6, 7, 8, 11, 12, 13, 14, 16, 17, 18, 19. So I have managed to avoid the fractions and still get a leading one in this position. As I was telling you, there was one more method of doing this. We could also have done R1 minus R2. That way I'll get minus 1, minus 1, minus 1, minus 1 over here. And then I could have multiplied the first row by minus 1. So either method is okay. Now let's try and get zeros in these positions. So the obvious transformation that I am going to require are R2 minus 5R1, R3 minus 11R1, R4 minus 16R1. My first row is going to remain the same, 1, 1, 1, 1. Second row is R2 minus 5R1, 5 minus 5, 0, 6 minus 5 is 1, 7 minus 5 is 2, 8 minus 5 is 3. Then we have R3 minus 11R1, 11 minus 11 0, 12 minus 11 is 1, 13 minus 11 is 2, 14 minus 11, 14 minus 11 is 3. And in the last row, I get 0, 1, 2, 3. So after getting the leading one in the first row, I managed to get zeros below that. The next step is to get a leading one in the second row. But fortunately, I have already got a leading one in the second row. So my next aim should be to get zeros in these two positions. And now I cannot use the first row anymore, otherwise I will lose these precious zeros. So I must make use of the second row to get a zero in these two positions. So it will have to be R3 minus R2 and R4 minus R2. So 1, 1, 1, 1, 0, 1, 2, 3, 0, 0, 0, 0. No more transformations are required. This is the echelon form of the matrix. Let's count the number of non-zero rows. There are two non-zero rows in this matrix. So the rank of this matrix is 2.
Sorry.